Okay then, welcome to yet another lecture of 2DM3. So I hope you are excited. At the request of some students, we are going to have a bit of ambience, some lo-fi if you like. If it becomes annoying on your side or bothersome, let me know and I can turn it off. So that's not a big deal. All right. So let's get started with today's lecture. Let me share with you my screen. Boop. All right. Dope. Let's begin. Okay. Alrighty. Actually, let's begin with a problem that someone asked. Someone asked to look at homework 3.2 and look at this invariant body. Whoop. Is this too small for some of you, or is it too big, or is it the right size, or what? All right. So it looks like it's too small. All right. Bueno. What about now? This is enormously huge for me. But is this good for you? The size is correct. Somebody says they like the size. All right. Okay. This is way too big for me. But anyhow, so let's just quickly go over this idea of Hoare logic. So we didn't get to do an example yesterday, so I just want to show you an example today. All right, so let's just do that. So just a quick reminder, you write a program that says, hey, there's a location X and I want to stuff some information E in that program, and I want to get some goal Q, okay? And this program will get you that goal Q if originally Q with E instead of X was true. All right, so not terribly sophisticated. Here's some laws that you should definitely know now. Cancellation of plus, cancellation of times. These are just some things you should definitely be aware of. If not, please do some integer exercises. So let's do a problem really quickly. So let's get rid of all this. Let's enter that. Okay. So we're right here. Let's try to solve this problem. What's going on? We want to write a program that says the sum of x and y is 20. No, he said there would be at least one word problem on it last lecture. Yes. So I just wanted to mention that. So yes, we want to write a program that says the sum of x and y is 20. And the program we have in mind is to increment x by 7. All right. So if we want to increment x by 7 and we want to have the sum of x and y is 20, what should we know beforehand? Assume you don't see this, all right? What will we have in it beforehand? So let's do that. Let's say x plus y equals 20. Remember, I'm starting at the bottom. This is really, really important. Starting at the bottom. Let me make a note of this for some of you. Ooh. Boop. Proof begins at Control Enter at the bottom. Then read up. Okay. So nope. Okay. Apparently I can't just leave these words here. I thought I could leave them here. I cannot leave these words here. That's quite unfortunate. But anyhow, so let's get back to the problem at hand. So we start at the very bottom, and we just want to show that this implication is going to be following using a program. And the program we have in mind is x becomes x plus 7. Okay, so I just set it up. There's nothing going on. We just set it up, right? So we have x plus y equals 20, and we want to use this program, and we want to find out what proviso will happen. Well, the only thing we know about using programs is to use the assignment rule. The assignment rule says x plus y equals 20. You just do a textual substitution. X becomes x plus 7. Okay? Notice how I'm working upwards. The only thing you can do now is textual substitution. And so you say there's an x that becomes x plus 7. and there is a y equals 20. Okay, and of course we can reorganize this if we like to make it more accessible. So instead of putting that there, I can say +7 right here. Notice right here the substitution is still okay because we have automatic associativity and symmetry. All right, great. And now I can say here's a fact that you like. 20 equals 13 plus 7. Okay, and that gives me x plus y plus 7 equals 13 plus 7. And then I can do a cancellation law. Cancellation of plus, and that will give me x plus y equals 13. Okay, notice how I worked up. All right. Now, does anybody want me to do another problem, or should we move on? All right. Do you want to see a harder one? It's no skin off my teeth. It's, we have other things to do. That's all. All right. So if you want, I'm happy to. It's no big deal. All right. I'm just looking here. Nobody's saying anything. So can we go over word problems? Yeah, David, let's go over a word problem. So let's solve this problem. You're on an island, and this island has knights and knaves, and they knights always tell the truth because they're noble and good, and that's what we want people to believe. And knaves, they're scoundrels, and they will always lie to you. They're always gonna try to pull one over you. So you see two people, and you're on this island because there's gold, and you wanna find out where the gold is. But these people won't talk to you unless you ask them yes or no questions. They're very picky people. All right. So you want to find out where's the gold, right? And so you say you get to a fork on the road, and the gold's either on the left or on the right, and you need to ask them a question to find out which way to go. So what do you ask? Before we get to that, let's try solving some of these simpler problems. Suppose you meet a person, and a person says, "Hey, me and my friend, we're both knaves." What do you know? What do you know about this person? Let's do some writing and find out. Boop. Let's get rid of that writing. Open up a new writing. Okay. So a person A says, we're both knaves. So let's write AA to mean person A is a knight. Let me try again. AA means person A is a knight. Okay, K-N-I-G-H-T. All right. I'm sorry, I'm gonna need more space than I have here.
Sorry to interrupt you, sir. Would you be able to turn the music down just a tiny bit? It's kind of like...
Yeah, we can definitely do that. Boop.
I think this is good.
Okay. So let's go back to the problem we were looking at. Here, I have a notebook right here. Let's just use this notebook since I have notebooks all opened up. So, all right. So we're on an island. Let's say, you know what? Let's use the notation. AA means person A is a knight. Okay. BB means person B is a knight. Okay. Then this is the main insight. Here's the insight. All right. A knight. Oh, that's how you spell knight. A knight always speaks the truth and only the truth. Likewise, a knave speaks false and only false, right? So we can rephrase this insight to say, AA says a statement S, if and only if, S is only if person my bad. Person A says S precisely when A AA is equal to S. All right. So a knight always speaks the truth. So if a person A, they say that the statement S, right, then that statement is true precisely when that person is a knight. All right, because if the statement is true, then that person must be speaking the truth, and therefore they must be a knight. And if they're a knight, they must be speaking the truth, and so S must be true. Okay. If a person says A and A is false, then that person must be lying. That's because they're a knave, and so AA is false. Okay, so this is the insight. Now we meet two people, PEOPL, and one of them says we are both knaves. We are both knaves, I think. We are both knaves. Okay. What do you know? All right. Well, here's what we know. We know that AA says we are both knaves. Okay. What does that mean? That means AA says I'm a knave and you're a knave. All right. Let's try a simpler one. Just because you guys aren't comfortable with we are of the same type. Because you guys aren't comfortable with conjunction yet. We are both of the same type. Let's try that. AA says we are of the same type. That means AA says I am a knight precisely when the other person is a knight, right? Or likewise, I'm a knave precisely when the other person's a knave. But because of the insight that we have, this is the same thing as saying AA equivales AA equivales BB. But this is the same thing as saying true equivales BB, which is the same thing as just BB. Hence, we know that B is a knight, but know nothing about A. Okay. So I hope you can see that these are just simple little puzzles, right? They're really, really simple puzzles. There's not that much involved. Some of them will require conjunction and negation, and that's what we're building up to. Yeah, and I think they're covered somewhere in the book as well, and we'll have some exercises on them. But they're quite simple. Feel free to discuss them as well in the online help. Okay, dokes. So let's go back to the lecture at hand. So so we just did this scenario. We did scenario 4. We are of the same type. All right. I recommend you try the other scenarios and post your answers in the course help, and we'll guide you if need be. Yeah. Again, the main insight is this: person A says S precisely when that person's a knight equivales the statement S as being true. This is the main insight to solving like almost all of these problems, and it comes from the fact that knights always speak the truth and only the truth. So this is the main insight. Okay, next. So let's get back to the lecture. So just as everyone's asking about the schedule, we're covering chapter 3 now. So please have chapter 1 done already. Chapter 2, if you haven't done it, that's okay. We'll come back to it next week. But we're starting chapter 3, so we're on 3.1 right now. All right, of the logical approach to discrete mathematics. Okay, and the things you really need to know for the midterm, these guys, you really need to know these. So besides the words like distributivity, symmetry, associativity, cancellation, you definitely need to know how these propositional operators work. Okay, you will definitely be tested on these. Yeah. All right. So just a quick reminder, equivalence is simply equality, but written with a different symbol. It's conjunctive instead of associative. So, and as I've mentioned repeatedly, you can read it as equivalent to, exactly when, precisely when, right? Very popular, people like to say it as if and only if. Okay, dokes. Yes, everything up till this lecture will be on the midterm. The other lecture that's happening concurrently at the same time as this one by Wolfram Call is also online, and I've linked to it using the abridged lecture notes webpage. And he's also given some hints about what's going to be on the lecture, on the midterm. So feel free to check those lecture videos as well. Okay, so as I said a moment ago, the operators have the same meaning, okay? But it's how we use them. One of them we treat associatively, so we change the parentheses, and the other one we treat it as an abbreviation for a conjunction, okay? So that's the main distinction there, right? Just in case everyone, question popped up, the other core of 2DM3 is doing the same content as we are. There's subtle differences here and there, but we're trying to use the same slide deck. We're trying to use the same homework. We're sharing TAs. We're trying to keep things in a line so that students can talk to each other and help each other out, okay? So feel free to watch the videos that Professor Wolfram Call has uploaded. I've linked to them from our abridged lecture notes webpage. He is an excellent expositor. So, I'll have fun watching this. Let's see. Okay. You definitely need to know how to do rigid matching. I'm not going to tell you if it's there or not, but you should definitely prepare for it. Everything so far is fair game for the midterm. Okay, ducks. All right. So this is the table of precedences. All right. As we've shown at almost every lecture, equivalence is at the very bottom. Okay. So this is the main reason why we want equivalence. We use equality all the time. This class is about an equational approach to discrete mathematics, and it's an equational logic. And we like to use equations, right? Linear algebra is all about solving equations, right? In one variable. And so equations are really, really important, but we have two notions of equality now because we're talking about Booleans and about other kinds of mathematical entities. And so to avoid many parentheses, we will use one of them conjunctionally and the other one associatively. Okay. All right. As repeated last time, we use these three main inference rules: Leibniz, transitivity, and substitution. And again, the numbers beside them, 1.5, 1.4, 1.1, are what chapter they're in. So chapter 1, all right? Chapter 1.1 has equation 1.5 for Leibniz, for example. As mentioned before, Leibniz lets us apply things inside, all right? So it lets us make equals for equals. Transitivity is what lets us go from the beginning of a calculation to the end of a calculation, okay? Substitution is like instantiation. If E is true for all variables, for all expressions X, then I can select some of them and it will continue to be true, okay? Equivalence, not in the book. If you have a newer edition, if you have an old edition, this is not in the book. This just says if I know that X is a theorem, and I showed that Y can be reduced to X, then I know that Y is also a theorem. Okay, that just says there's essentially that all theorems are the same. All theorems are equivalent, right? So some of you might have theorem 3.4 that says all theorems are equivalent. That's essentially another way to mention equivalence, right? Equi for the same or equivalent. Okay, ducks. Okay. Now, because equality is transitive, right? 1.4 right here. This means we can start off. We can do we can do E0. Then we slide down the right-hand column to E3. And the fact that we can slide down the left-hand column and the result is going to be equal is, again, transitivity. And that's why we care about this rule. It lets us write our proofs this way. Okie dokes. So I'm just going over some of these facts quickly because I've been repeating them over and over. And don't worry, I will continue to repeat them over and over when we add new symbols to the left-hand column. So besides equality, at one point we're going to have other things like implications, or as you saw a moment ago, how we had programs happening there. Okie dokes. Okay. So equivalence, a moment ago I showed it to you. Let me show that again. Right here, equivalence, the very last one says if X is equal to Y and X is a theorem, then Y is a theorem. And that's So some of you that have the older book will see the definition of a theorem as either an axiom, the conclusion of an inference rule, or this grayed out part that says if x is equal to y, and you know that x is a theorem, then y is a theorem. That's what that gray part says. Okay, dokes. The important thing here is we're proving theorems by changing symbols around. It's like when you play Monopoly, right? You move symbol, you roll the dice and you do things, but you don't get to pick up your player and move him somewhere because you feel like it, or you argue your way out of it. Instead, you're like, what do the rules let me do? Right? I'm just playing a formal game and I move symbols around. I don't get to ask, what does this mean? Why? How? Right? Like, so x equals x is a fact. We don't ask, why is it the case that everything is equal to itself? Right? What are the situations that make it that a particular chosen value is equal to itself? What does equality mean? All right. So these are not questions.
Prof, I think you're muted.
Sorry about that. I don't know why I got muted there. Okay. So I was just saying before I accidentally got muted that we're to find out if a formula is true, we're not going to plug in all possible values. All right. So that's what this box says. We're not going to evaluate to find out if things are true. We're going to calculate instead. All right. So it's without trying to find out if it works for all possible inputs, for all possible variables, for all possible values. Instead, we're just going to move the symbols around according to the rules of the game. So the rules of the game are right here. These are the rules of the game. And to make the game more fun, we add more rules as we go on. So here's the main rules we have. All right. So if you want to check if something is true or makes sense, you use these rules of the game. Right? And we said those rules let us play the game by drawing it this way. We can draw things as if they were equations. We draw something at the top, we slide down, we draw something else at the bottom. Okay, so that's what those rules let us play the game this way. Right? They give us a different kind of arena to play the game. Okie dokes. So, of course, you play a game, you have some rules, but you want to have some main characters. So some of our main characters are going to be this operation called equivalence, right? And here's the main properties about it. It's associative, as mentioned earlier. And whenever you see it, you can flip its arguments around. It's symmetric, just like addition, right? So let's write that down. Whoop, x plus y, enter, equals y plus x, right? So just like this property. I didn't save it, but that's okay. All right, and the theorem is really simple, right? We have to show that P, let's prove this theorem that says P equivales Q equivales Q. No problem. We swap two pieces. That's all. We swap the, what are we swapping? We swap this part with this part. Okay, so this one goes here and that one goes there. Okay, so we swap them and now this thing is just symmetry. Right? And this is a theorem because of equivalence. Equivalence says if you want to prove some result y, you reduce it to some other result here, x, and we know that x is true. Okie dokes. All right. And I mentioned last time we can define true to be this equality of q equals q, right? And then we can read it either way we're interested in. We can read it. Either. Oh, sorry about that. We can read it as true equals q does nothing, like addition. All right, so let me write that down. Oop. It's like 0 plus x equals x. And so that's one way you can read it, right? Another way is to say, you know what, everything is equal to itself, and that is a true fact. Right? So different ways to read it. So if you read the bottom one, we're defining true to mean q equals q, whereas the top one says true is the do nothing element. It's the identity element. So I'm going to be using that word from now on. Identity element, symmetry, associativity. You should definitely be comfortable with these words if you've been following along and doing exercises. Okay, next. All right. And we got to last time, we can show that true is a theorem, right? So what we do is we say, all right, true. Well, if I just replace right here, if I just pick Q to be true, then I get true equals true, right? If you remember from, not remember from, just remember from, one of the homeworks had a thing like this, but we'll get back to it later on. Anyhow, so we use this fact right here to get true equals true, but we know that true is the same as Q equals Q by the same fact. And so we have shown that true, right, is the same as true equals Q, and by equivalence, this is a theorem. Okay. So here's some other facts about our main player. All right. So our key player is this equivalence character. All right. So some key facts. True is a theorem. Reflexivity of equivalence. So everything is equivalent to itself. This is just an idea of how to do things. We've talked about it before. Start with the more complicated side and simplify. And this is the meta theorem I talked about a moment ago, how any two theorems are equivalent. This is essentially what equivalence says. Okay, next. So notice we have rules for a game, and then we said here's our main character called equivalence, and here's some properties about equivalence. Right? And using these properties, we were able to derive some other things. Okay, next. All right. So let's see. Yes, inequivalence is associative. I think that's on one of your homeworks, actually. So somebody else. So now that we have a notion of true, true is just Q equals Q. So now we say for any Q. So now we can say false is the negation of true. Okay. So we're introducing a new player. Before we introduced equivalence into our game, then we said, hey, this common scenario of P equivalence P or Q equivalence Q, these are all the same. Let's name those common scenarios as true. And now we say, all right, what about when you negate true? Let's name that guy false. All right. And here's an interesting relationship between negation and equivalence. They commute, right? You can move the parentheses from the outside. I don't need to use my hands, I can show you. Let's use that shape. Let's keep that. So the parentheses are right here on the outside. Now the parentheses are on the first guy. Okay, so I can have not, then a bunch of parentheses, or I can have not P in parentheses, and then everything else. Okay, so the book calls this a distributivity law. That's not what the word distributivity means. I think they were trying to stretch the meaning there, playing code names, if you will. So we won't use that name in this class at all. We'll just call it commutativity, commutativity of negation with equivalence. And again, you can read these things different ways if you like, right? You can read it as defining what it means to negate an equivalence. So not an equivalence means just not one of them. So what does it mean for two things to be the same, right? Well, in particular, we're talking about Boolean values. Remember, equivalence is for Booleans. This guy is for Booleans only. So if you have two Booleans, true or false, what does that mean for them to be different? Well, there's either true or false. And to say they're not the same means one of them has to be the negation of the other. There's only two, right? So the fact that it's the fact that it's not these guys are equal, right? Just means one of them is the negation of the other one. That's all, right? And if you think of it that way, you're like, oh, that's obvious, right? I only have true and false, and if I have two values and they can only be true or false, and these two values are different, then one of them has to be true, Q, and the other one has to be false. So they have to be opposites. Not too difficult. And then you can always read it as an algebraic law, which says, hey, whenever you have a weird situation like this, with P's and not P's, you can absorb some of those things away and get just a Q, right? So that's the nice thing about having an algebraic formulation. It lets you read things differently. Okay, and now we're going to get to the last fun character before the midterm. This operation is called in equivalence, okay? And we just define it as the negation of an equivalence. Okay? So again, equivalence is equality on the Booleans. Inequivalence is inequality on the Booleans. That's all. So nothing terribly, foreign or new. Right? So here's a theorem. If you have a not in an equivalence, you can take that not and shove it to the other side. Right? You can move it all the way here. So I think your homework has a problem like this, which says if you have the inverse, you can move the inverse to the other side. So these are called connection rules, or Galois connections, if you like. We'll get to that name later on in the future. In particular, it means if you have a negation, right, on both sides, you move it to the other side and cancel them, and so you have an elimination rule or an injectivity rule. Don't worry if you're not comfortable with these names. Right? Another thing we can show is that not P is equivalent to P. Let's show this. We're doing a lot of talking. Let's show this. What could go wrong besides everything? All right, so let's show this. Let's show. What do we want to show? We want to show not P equivales not P. Okay, so let's show this. Whoop. All right. What we could do is we could say. All right, not P, right? Let me just show you the slides so you can see them for quick reference. We have this main rule, so we'll use that. And we have definition of false over there. Okay. Oh, this is trickier than I remembered. Ugh. Let's see how reasonable it is. L naught P. So this is equal because of some. Oh, I have access to calc check. Why am I being silly? Calculation L naught P. Okay. I'm not in a notebook that knows how to use these things. It's unfortunate. Let's go somewhere else. Okay, here's a notebook. Calculation L naught P. Okay, so here's the thing we have. We want to simplify. The only things we know are, for example, the identities. So let's say P equivales true. See where that gets us. I don't know where it will get us because I'm also shooting in the dark right here. It's not like I planned this. Let's see where that gets us. Well, we know because of commutativity that goes L naught P equivales true. So we have somewhere identity of that, and here we have commutativity of that guy. Okay, everything's good. Muy bueno. We have L naught connection, which lets us move things around. L naught P slash equivales. Nope, that one goes over here. L naught true. Okay. And what else can we do? We can say commutativity of that guy equals L naught P slash equivale slash L naught true. And then we can say no problem. We have the identity of that guy, and that's L naught P equivales true equivales L naught true. Let me add in some parentheses to make it clear what I'm talking about. This is what I'm saying. Let's do a proof check. Muy bueno. And now let's do connection one more time. And that will give us P equivale slash not true slash equivale slash not true. And let's do the identity of that guy to get P equivales true. And then let's do the identity of that guy to get P. All right. So, so that worked. This is I probably did some silly stuff. This is way too long for such a simple result. I probably did some silly stuff because I didn't plan for this. Like all these identities could have probably been simplified, or I could have brought these commutative earlier. But anyhow, I just wanted to show you it's not a big deal. Some of these proofs it can be quite easy, and apparently fun when you get all this green. Okay, next. Alrighty. So yeah, so you introduce all these players and you can play all these little games, right? So it's a lot of fun. So definitely before the midterm, I would highly recommend you try playing the game and prove these results. Okay, there's a lot in the book, but you know, practice and so you can get more comfortable, right? So you can get a bit faster. You know the names. You know how to do them. Like I did that a moment ago. So just some stuff to help you out. Okay. So now we have this new operation in equivalence, and it inherits all the other properties from equivalence because it's just a negation, right? So no, not a lot happening there. So in particular, you can swap arguments as before. Parentheses, you can put them in the left or on the right, so they don't matter. It's mutually associative, so this is pretty neat. This mutual associativity is like when you work with addition and subtraction, right? So you can say k plus m minus n, and this is not vague, right? If you think of it as k plus m minus n, right? Or if you think of it as k plus m minus n, either will be fine. Okay, ducks. So that's a really nice one. This last law is kind of special, interchangeability. You can take the operator in equivalence and just move it over there, right? So really, you just bring in the negation because in equivalence has a negation. That's all it is. You unfold to get that negation, and then you push that negation using the connection law to the other side. So nothing too difficult. Okay, that's just some fun stuff to try out. Just want to keep an eye on the time. Okay, so here's a simple proof. This time all typed out for your convenience. So we want to show that P is distinct from Q is the same thing as Q is distinct from P, right? We just unpack to get that negation out. Then we apply the symmetry of the underlying operation. Then we repack, right? So this is in the book. This is called the fold-unfold strategy. When you meet a new operation, so hint, hint for the midterm and stuff. When you meet a new operation, you say, all right, is it defined using earlier operations? If it is, and I'm more comfortable with the earlier ones, like equality, then let me go use those instead of inequality, inequivalence. Work with those, and then call on the definition later. Okay, ducks? So this is page 48, this idea of unpacking the definition, doing the work, and then repacking the definition. Okay, ducks? So we unfolded at the very first line to get at the underlying definition, all right here. Then we did some work, then we came back, right? So nothing too interesting. So here is our problem again, and we tackled some of it. Some of these are trickier to solve than others. So this is the one we did at the very beginning. Knight's always the truth, and we said if we're of the same type, what do we get, right? So I just did it really quickly for you in earlier to show you my thought process. But the key insight is if a person A says a statement X, then that person is a knight precisely when their statement is true, right? And if their statement is false, and that person said that statement, then that person must not be a knight. And if you're not a knight on this island of knights and knaves, you must be a knave. Okay, so there's a formalization of this coming up that you'll see in CalCheck notebooks, where the phrase says is a binary operator, and you'll be able to actually check these things yourself. But just as we did before, A says we're of the same type, so I'm a knight precisely when you're a knight. And then we just reassociate, right? And then we just cancel. A is a knight and A is a knight. This is true, and true is the identity of the whole thing, so we just get that, right? And of course, we could reread symmetry to say, hey, if you have this first triple, you get the last one. Okay. Somebody's asked a question. So some of the problems we might give you will probably be, you know what, here's the first line. Oh, sorry. Here is the first line. Simplify as much as possible to get down here. Right? That might be what we would do. We might say, here's the first one, simplify. Right? And you can only simplify if you're familiar with the laws. Right? So if you stay here, well, you could have simplified further. Right? So this is what we might test you on. Okay. Now, knaves always lie, right? So what if we consider an alternate formulation? Somebody asked, what does it mean contextually when you say BH? So I know this is true. The very top line is true. And I simplified, and I got this, right? But that means this is true, and I went all the way down, and now I know this is true. Okay? Because I know this is true, BH, that's the same thing as writing AH. Now that means I know that B is a knight. Okay? So I think we did this a moment ago as well. Here maybe? Here? Yeah, and so we ended up with B is a knight. So this is the same calculation we did a moment ago, like at the very beginning of lecture. So we know that B is a knight, and we know nothing about the person A. Okay, next. Let's go back here. Okay. Now, knaves, they always lie. If we ask if the person saying it is a knave, what will we know? We know that the statement, as before, right? The person is a knight precisely when what they say is true. That applies to everybody, not just knights, right? So if we, just for the sake of argument, if we say A subscript V is A is a knave, then it's the same schema, right? Except you have a negation, right? But of course, in case it's not clear to some of you, not A V V is the same thing as, or let me do it the other way. AV is the same thing as not a H. Okay, you're a knave precisely when you're not a knight. Okay, so hopefully that makes sense. Right. So because you're a knave precisely when you're not a knight, right? You're a knave precisely when you're not a knight. That means whatever you say is going to be true precisely when you're not a knight. That is, you're a knave. Okay. So again, A says some statement. This is knavehood, which is what we have. All right. And then we just simplify using the negation laws with equivalence and then symmetry. So there's nothing terribly complicated about it. And all we get is the result is if A says we're of the same type, we know that the person B is not a knave. But what does being not a knave mean? It means you're a knight, which is exactly what we saw a moment ago, right? So if you choose to formalize the problem from the perspective of knighthood or knavehood is up to you. I prefer formalizing things from knighthood, right? Because then I have less negations to worry about. But it's important to know both perspectives, right? Notice in this proof, the unfortunate thing is we repeated this part here, then we repeated it again, then repeated it a third time, right? We didn't do that repetition when we did this one right here, right? We kind of simplified as much as possible, and there was little repetition, all right? So this is mentioned in the book. If you have an equality and you want to show this equality is true, and you prove your thing and you're done, maybe notice that one side is never changing, and you're always manipulating the other side. So maybe just start with the other side and simplify that till it looks like the side you haven't touched, right? So that way your expressions are not flowing off the page. So some people in CalcCheck will have a big long equation, and one side they never change, and they do this for like 10 lines, and it's so long because they have a long side they never touch. So just be aware of these things. I think it's the book chapter 3.1 has some principles on writing proofs. So I recommend looking at that if you have the time. Okay. So this is the same proof as before, but the boxes now are gone, right? And we can simplify directly to find out the person B is not a knave. Okay. So again, if you're not comfortable with these things, please read chapter 1 and section 3.1, at least chapter 1 and section 3.1 for the midterm. Okay, and please do all the exercises. Okay. So as I was talking to some people before class started, it's like playing a game. If you don't know how negations can be moved around, if you're not comfortable with how I move quickly from equals to equivales, or how I can use associativity under the hood or symmetry under the hood, if these things are complicated for you, you're going to have a tough time writing proofs with all that time pressure for the midterm. So I recommend you spend the weekend if need be and do the exercise books, all of the exercise books, do the homework books, ask questions, right? Some of you are tempted to use Google and go ahead, look at Google, that's fine. But I would like to remind you, you have a 50-minute time limit, and we wrote the midterm with the intention that you're not going to waste time looking at the book or looking at Google. And if you do waste time that way, some of the words, so I tried Googling them myself just to make sure. And yeah, not a lot of people use the words that we're using. So sometimes you'll find some things that will waste your time and won't help you. So it's best to just do the exercises that we've written for you. And there's homework 4 up, and it's supposed to help get you ready for the midterm. Okay, dokes? So it's written, it was written in parallel with the midterm. So that way the problems are kind of go in each other. Everything we've covered so far is fair game, all right, including today's lecture. So just for the future lecture, we are going to continue with chapter 3. We're going to talk about disjunction, right, which just means the OR operation. And then we can, when we have OR available to us, we can talk about different kinds of knights and knave problems. And then hopefully we'll get to more ladies and tigers and other kind of linguistic puzzles. Conjunction for and, right? Implication for if then else or conditional statements. So the class moves at a fast pace because there's a lot of simple things we just want to get out of the way and get to interesting problems. So that's why we have a lot of exercises between the homeworks. We have lots of exercises and homeworks between lectures, right? They reinforce what you learned, and the idea is to move on. We might start with natural induction. Don't worry if you don't know what this means. It's just more linguistics, right? Linguistics is a big part of computer science. So natural induction and induction in particular is a way to specify expressions or grammars of a particular kind, and they're quite useful in mathematics and programming. Okay, ducks. So that's all I've prepared for today. I think I would like to talk about, what would I like to talk about? Yeah, actually, you know what? Yeah, that's all I've prepared for today. If we'll finish on time today. We'll finish on time. I will answer some questions if you like. So I will be here for the next little while to do that. Let me know if you have any questions, concerns, or queries. And if you're leaving, have a fantastic Friday and all the best. Okay.